Okay, so in the last video in this series, we were here and we talked about velocity, deriving velocity on a trajectory. Okay, and see, yeah, so like on trajectory, and then change the velocity, and from there we got this, and then we got the instantaneous acceleration, and from here we kind of said that this will eventually feed into f at some instant t equals to constant mass acceleration a. So it's going to feed into this, and this will be at a constant at a particular time. So this is instantaneous. They are not going to use average acceleration. They're going to use instantaneous acceleration, and that's something that a lot of students miss it. They just think acceleration, that, but they are not thinking instant by instant. I want you to start visualizing things instant by instant. Okay, so today in this video, I'm going to complete this. I ran out of time last one and abruptly ended the video. So let's complete this theoretical discussion of special motions. And this is what almost, I'll say 75% of questions come from this. And then there will be general motion. Just going to do later, general motion, not now. So let's look at special motions. Okay. So of course for motion you need a with respect to a frame. So there will be a frame which itself is fixed. So frame is not moving. Okay, so frame is fixed. So just bear with me because we will talk about frame moving in a future video. So this is a frame, z, x, and y, and maybe your particle is over here at some time t. At some time t, it's over here, and it's moving at a constant velocity. So what's given is given this velocity of this thing at time t is constant. And if this is a vector, then this guy has to be some vector c. Okay, some constant. Let's call it k, vector k. The letter c will be used by speed of light future. So this is not changing. So this, we've been talking about writing vectors, right? So what this means is you have a xt and vyt, vzt. So it's a collection of three things and in Cartesian frame. And so this will be a collection of these three things: x part, y part, and z part. So we will talk about vector as we go along, not going to have very special treatment vector. So take so what this will be, if this equal to that, then each of these will have to equal to each of these. So it leads to usually three equations. Vy of t, ky, vz of t is kz. All right. Okay. then you already know this is equal to dx dt equals to kx. This is dy dt equals to ky, and this is dz dt equals to kz. Of course, this can be integrated. This is constant. This is constant. This is constant. So this will means dx equals to kxt dt, and so if this has to be integrated from 0 to t, or if you set t1 to t2, x1 to x2. So these go together and this go together. So this is x2 minus x1 equals to kx t2 minus t1. So if you take a t1 equal to 0, say t1 equals 0 and t2 is some arbitrary instant t, and let's call this guy x0, x1 x0, and at this time this will be some arbitrary time. So this will be x at instant t minus x0 equal to kx t. So it tells you how you can actually change in coordinate based on values of kx. Similarly, this will lead to y of t, y0 equal to ky times t, and this will lead to z of t minus z0 equal to kz t. This is just a straight simple example. Let's look at, you're driving a car at 30 miles per hour, and this is t is in hour. Maybe you were here at t equal to 0, and you want to know maybe 0.5 hour, how far have you gone? Well, this is x, this is x, and this is y. So this point in time will be here. So the question is where is this, how far it is, okay? And of course this guy has y equal to 0 and z equal to 0. It's not going anywhere into y and z. So we just look at, so these guys are doing so so what it is kx. It says velocity was constant, k constant. So what this is this guy is telling me, so this is 30 miles per hour 0. So this is kx. So ky is 0 and kz is 0. So right from here, just algebraically, you don't, I know this is a really trivial problem, you can just don't go through this, and then x at 0.5 hour minus x at 0 hour is equal to 30 miles per hour times 0.5 hour. So this is what we want, and this is, in this situation, is 0. So this is 15 miles. So you know it's going to be 15 miles. I just want to show you that these equations are very easy to use. Okay, So this constant velocity. Constant velocity is very simple. Let's look at another example. Let's see z is 0. So we're gonna just, it's in the xy plane. XY plane. This is not gravity, because this is outer space. Imagine outer space. Don't worry about gravity. So something is going 30 miles per hour that way. It will go in that direction forever, okay? Imagine. It's been going like this forever. So at t equals 0 was here. At t equals to 0.5 hour, on the path, it would have gone, already know 15 miles. It will be 15 miles along that path. Let's see, this is let's say 60 degrees. Let's call it 60 degrees, okay? So if you look at this vector, 30 miles per hour, 60 degrees, along the x-axis and along the y-axis. When you drop it here, this will give you v sub x. When you drop on the y-axis 90 degrees projection, this will give you v sub y. Why? Remember position vector. So let's look at a position vector. X and y. Let's say some particle p was here and its coordinate was, it is vector r p. And so we could write in terms of its coordinate by, this will be x by projection, and this will be y by projection. And that's how r at p we were able to write x, y. And so here we want to write v equals to vx, vy. So this, we follow example of project all the velocity, all the vectors. By the way, all the vectors, as long as you know how to deal with this position, it's exactly the same way all the vectors will work. All right? Let me repeat. If you know, you understand this, and you know all the math back and forth of a vector, position vector, you pretty much have to just copy the same math in all other vectors. So if you had a, say, vector, again I'm going to just do z part, it doesn't exist. So suppose you had a force vector and you angle theta with the x-axis. So you know force will have fx, fy, fz. So how do we get these guys here? We just project, just like here. Just you project. This is going to be fx. This project, there's going to be fy, and similarly for fc. So this is the key. Use it, okay? So I do this, and in this triangle, obviously, if this thing length is v without the arrow, means length of vector or magnitude. Either one is fine. It's just name for this distance. Name for this distance for a vector will be will be, this is velocity, is not a length actually, it's just length of the arrow. So if this is Vx and this side parallel to that is Vy, then you can, and this angle this, so Vx will simply be 30 miles per hour cosine 60 degree, which is half, which is 30 times half is 15 miles per hour, and Vy is 30 miles hour sine 60 degrees, which is square root of 3/2. So 15 is square root of 3 miles per hour. And this V is the magnitude, so the V is also speed. So this is the speed, and this is the path it's going to take. So by the time it gets over there, this is going to be this total distance. Total distance will you can, so the path is known. So it's going on this path, and speed is 30 miles per hour, and delta t is 0.5 hour. Then of course, remember speed definition is ds dt. S is the distance traveled. So if you bring it over there, and this is constant, so ds will be v dt. So if I integrate, and if this is constant, it will come outside v dt, v not a function of t. This is going to come out as this will be the total distance. S equals to v, and this is total time, 30 miles per hour times 0.5 hours is 15 miles. So we know this is going to be 15 miles, same as before, same as this example over here. Yeah, same as this example, but this is going in not x direction but this direction. So you want to know how far it go in the x direction and how far it's going to go in the y direction. So how far in x direction? Well, there's Vx equals to dx dt. So dx equals to Vx dt. Integrate. This comes out because constant is Vx dt. So constant. So total x, delta x, total x is going to be Vx times delta t, and say 15 miles per hour, 15 miles per hour times 0.5 hour, 7.5 miles. So it goes 7.5 miles this way, and how much there? Well, you know this and this, you can figure out that by Pythagoras theorem. So how far in y direction? Well, it went x here, delta x here, delta y here, and it went 30 here, 15 here, and this went 7.5 here. So it doesn't matter what the angle is. So delta y will be square root of 15 squared plus 7.5 squared. So you can do it this way, or you can do this way. You can do Vy equals dy dt, and just follow this. This should be delta y equals to 15 over 2 is square root 3 miles. 7.5 times square root of 3 miles. And this, if you work it out, is going to be, it should be the same, because you can pull 7.5 outside. So this will give you 1. This should be minus this, minus that. No wonder I got, so this will be 2 square minus 1. Okay, so that's that's the constant velocity. The next one is constant speed. Well, the constant motion is another really simple one. So V ds over dt equals this, where s is distance covered along the actual path of motion. So if you're going around, say, some kind of oval thing, and you start here, let's call it s equal to 0, t equal to 0, and you mark it. Here you have time t. So what is the distance cover? What is the total distance cover? Well, this is integrated, that's all. V is constant, V constant. So it just S is equal to V times total time. This is really simple. So suppose you went like this in the same one, and it's completely independent of how many rounds you go, right? So s equals 0, t equal to 0. Here you went at constant. You're just going around constant, and came back, keep going, multi rounds. And so say you did n rounds, and you came back the same place at t. So how much distance did you cover? S equal to V times delta t. So delta t is the t. You came back t minus t0. Is Vt. And this S is n rounds, and whatever it is, if you go all the way around once, let's call it d once equals to Vt. So if this was a circle, and often this is tried, if you have a circle of radius r and you start over here, t equal to 0, and you went around n times, and then you ended up t equal to t, let's call it capital T here. So n times 2 pi r, this is once go around, will give you v times total time it took. Okay. Of course, that will means time for one round once around just 2 pi r over v when n is 1. That gives you time for once. And this is an important formula, and some people can just memorize it, but you don't have to memorize it. You just say, well, I want 2 pi r and took me t for once, and that must be the speed. This must be the speed because constant. If I went constant, this was the case. If I didn't go constant, if the speed was not constant, see, it becomes very complicated. If speed not constant, then you're going to run into trouble like this. You're still going to have v equal to ds dt equals to v. Let's write like that. Bring it over there, and it's a function of time now. Then ds equals to v, a function of time, dt. So then I really need to do the integral. So this is the next equals to delta s net distance I went, say from 0 to t, capital T maybe, must integrate. For that, I really need to know that this function, I need to know how I was changing, how my speed was changing. Okay? So this is the complication. That's why we're doing constant speed. And this is often the case in test. Tests often test this. Okay, let me give you an example. Maybe you went 50 meter at 10 meter per second, and then you went another 50 meter but went 20 meter per second. So in each one of them you had a constant speed. Then say, okay, from here to here, what's your average speed? This is an often asked question, kind of thing. Okay, so how do you do? Well, this will be what is the distance you took, and if t was 0 here and t was t here, then average speed will be the distance you took over total time. So you need to figure out distance. You already know it's 100 meters. So you already know 100 over here, but you don't know this. So you have to figure out how much total. So you got to figure out time for this guy and time for this guy, and then add them up. So time for this guy, because constant, we can just use. You can just use this because constant s equal to vt. So this for this, we got t1 equals to S1 over V1, and S1 is 50 meter over 10 meter per second, so this is 5 seconds. So T2 for this part is 50 over 20 is 2.5 seconds. So this whole thing took 7.5 seconds. So this would be the average speed. This is not equal to 10. It's not equal to 10 plus 20 over 2 equals 15. Is it 15? Let's see. I mean, it doesn't have to be, but it might be because we're just doing same distance. So we check it out. So 100 over 75 times 10. So 25 times 3, and it's like that. So we have a 40 over 3 . So it's not that. See this? You have a different average speed. So this is something that you test a lot. Okay. How about if you went 10 meter per second for t equal to 0 and maybe 2 seconds. But you went another 2 seconds, but this time you're on 20 meter per second. So now, what's the average speed? Well, you might say, okay, let's do the same thing. Find the total distance, find the total time. Okay, total distance. So total distance is not given. Total time is 4 seconds. 2 seconds here, 2 seconds here. I mean, so this was 2 seconds, and this was 2 seconds. So, so how far did you go here? So again, this is constant. This is constant segment. So this must be 20 meter mark, right? 10 times 2, 20 meter mark. So this distance will be 2 is 40 meters. So this will be, this is 20 meters and this is 40 meters. The total is 60 meters. So V average here is going to be 60 over 4, and this is 15 meter per second, which would be the same as if you did 10 plus 20 over 2, just average the speeds. And here this is equal to that, and why? Is because each one of them, 2 segments, use same amount of time. So to trick you, if I were making a question, I'll say, oh, go 2 seconds here, but maybe just go 1 second here, go 20 meter per second, 10 meter per second. Now do the average speed from here to here. We do exactly the same thing, and you're going to find out. So total time here is 3 seconds. Total distance here is d1 plus d2. d1 is still 20 meter for this guy, but this was also 20 meters, 40 meters, So now average speed is not 15 meter per second. Instead, it is 40 over 3 meter per second. Cool, right? Cool. Okay, so that's the average constant speed. A lot of constant speed trickery go on because people are careless. The last one is constant acceleration. And I'm going to defer this to definitely tomorrow. That's a long topic. We want to be able to talk about gravity, motion, vertical motion, gravity. See you. Bye.